Let's look at an example of the logistic equation. So we'll consider dp dt equals p times 1 minus p. And this is the logistic equation with k equals 1 and m equals 1. We'll also add a generic initial condition that says that the population at time 0 is p0. So we're going to solve this equation, and we'll solve it using the technique of separation of variables. So remember, to separate variables, we put all the p's on one side and all the t's on the other, and we'll get the integral of dp over p times 1 minus p is equal to the integral of dt. Now this integral on the right-hand side, that's very easy to do, but the integral on the left-hand side is a little harder. In order to compute this integral, we need to use the technique of partial fractions. So I'll remind you how that works. So the partial fractions works by looking at the integrand here. The integrand is 1 over p times 1 minus p. So we look at that integrand, and we assume that that integrand splits into a sum of two fractions, a over p plus b over 1 minus p. Now the goal will be to figure out what a and b are. Well, how would we do that? Well, we find a common denominator. So we multiply the first fraction by 1 minus p over 1 minus p, and the second fraction by p over p. And once we've done that, we have a common denominator. And so the two numerators must be equal. We must have 1 equals a times 1 minus p plus b times p. Now simplify that a little bit, and you get a plus b minus a times p equals 1. Now there's no p's on the right-hand side here, so that means that b minus a must be 0, and a must be 1. So the conclusion is that a equals 1 and b equals 1. So now that we have our partial fraction decomposition, we apply it to the original integral. So this integral of dp over p times 1 minus p becomes the integral of the sum of the two fractions that we tried to decompose into, 1 over p plus 1 over 1 minus p. So it's the integral of dp over p plus the integral of dp over 1 minus p. Now these two integrals I can do, they're not too hard. The first one is the natural log of p, and the second one is negative natural log of 1 minus p, the minus sign coming from the chain rule because there's a minus in front of the p. Now I won't worry about putting absolute values in front of these p's right now. Now I can use the sum to ratio rule for the logarithm to write that as the natural log of p divided by 1 minus p. Now let's continue this on the next slide. Okay, so here we are on the next slide. So we're trying to solve the logistic equation here, and we separated variables to get these two integrals. And the integral on the left-hand side was hard, so we applied partial fractions, and we figured out what it is. So we can now integrate both sides of this equation, and we get the natural log of p divided by 1 minus p is equal to t plus some constant. Now, you may have noticed before that I didn't put a plus c when I did the integral for the left-hand side, and that's because I'm just going to include it in the plus c from the right-hand side. Two arbitrary constants are the same as one arbitrary constant. So the next step is to begin to solve for p. So I'll exponentiate both sides. And so I get p divided by 1 minus p is equal to c e to the t. It's not the same c now. I've just exponentiated and used the exponential rule, but I'm still going to write it as c because it's still an arbitrary constant. Now I do a little algebra. This might look a little fearsome, but just get out your scratch paper and do it. And solve for p, and you'll get p of t equals c e to the t divided by 1 plus c e to the t. This is excellent. We are almost done, and some people would stop here. But remember, we have an initial condition, p of 0 equals p0. So let's see if we can get rid of these c's and instead write everything in terms of p0. So we'll plug in the initial condition. We get p of 0 equals c divided by 1 plus c. So I just plug in t equals 0 into the two e's here, and that's equal to p0. So again, a little bit of algebra, and you'll get c equals p0 divided by 1 minus p0. So we need to plug that value in for c in the equation above. So do it. Simplify a little bit, and you'll get p0 e to the t divided by 1 minus p0 plus p0 e to the t. This is our final solution to the logistic equation with this generic initial condition for the initial population. As a little bonus before we finish, let's look at some graphs of these solutions for various values of p0. Now what I did here is, rather than graph a bunch of different values of P0, I made an animation where we have a slider where we can control the value of P0. So what I'll do now is I'll change the value from P0 equals 0 all the way up to P0 equals 2. So we see if we start off at P0 equals 0, the solution stays 0. Now if we bump up to some beginning population, which is something above 0, then we will grow and begin to level off at 1. And if we start up a little higher, we still level off at 1. If we start at 1, we stay at 1. If we go up above 1, then we'll come down and, again, level off at 1. So this is hopefully the behavior that you expect, because 1 is the carrying capacity for this particular logistic equation.